Hi, this is a short video about electron spin and Stern-Gerlach experiment by Seok and Mikhail. Let me start with the experimental setup of Stern-Gerlach experiment. First, silver atom is ejected from the oven, and only silver atoms of horizontal directions are collected by the small slit. Silver atoms are then introduced to the inhomogeneous magnetic field, and silver atoms are detected by the detector. If silver atom has non-zero net angular momentum, then the direction of the atoms will be bended by interactions with the magnetic field, and they will be detected either in positive z or negative z directions. So why silver atom is used? First, silver has electron configuration of krypton 4d10 and 5s1. It has net orbital angular momentum of 0. How can we calculate the net orbital angular momentum if we have 47 electrons in the atom? For many electron systems, we use Clebsch-Gordon series to calculate total orbital angular momentum. Let's say L1 and L2 are the individual orbital angular momentum of two different electrons. L1 and L2 are vectors, and the total momentum is the set of coupling those two vectors. Then possible set of total momentum has maximum value of L1 plus L2 if L1 and L2 are in the same direction. And total momentum has minimum value if they are in opposite direction. And the value should be absolute value of L1 minus L2. So the possible set of coupling those two are from L1 plus L2 to the absolute value of L1 minus L2. Now this looks complicated if we have many electrons, that we have to consider consequent coupling of momentum. But specifically for the closed shell, total momentum is always 0. This is because if we vector sum all the individual angular momentum, then due to the spherical symmetry, we always get 0 angular momentum. This is the reason why we only have to consider electrons in the unfilled orbitals. Now let's look at the example of silver. It has 1 electron in 5s orbital, and other 46 electrons are all in the closed shell. So there is no coupling of orbital angular momentum, and the total orbital angular momentum is just 0, since electron is just in s orbital. Now there is another example of phosphorus, but I'll skip it here because this is not a scope of our video. Now coming back to the Stern-Gerlach experiment, if you use classical mechanics, that angular momentum could take any value. It will show continuous line on the detector as the left-hand side figure. And if you use quantum mechanics, angular momentum is quantized, but for a silver atom, we know that the total orbital angular momentum is just 0. However, according to the relativistic theory of electron by Paul Dirac, electron has been predicted to have intrinsic angular momentum. So according to the quantum physics, even though orbital angular momentum is 0, there should be some distinct bands shown in the detector due to the intrinsic term, so-called spin. So which one was correct? What they really observed was 2 distinct points of atoms, which is consistent with quantum mechanics. This implies that there is an intrinsic angular momentum of electron. However, this experiment needs a specific condition about the intensity of silver beam. If intensity of silver beam is too high, then the frequency of collisions of atoms would be also high, and thereby bands would be blurred. Even Stern and Gerlach first observed the continuous band, which was thought to be the classical expectation, but later they knew that the intensity of silver beam was the problem. So they changed to the low intensity beam, and the result was 2 distinct bands of atoms. So the key of Stern-Gerlach experiment is to use the silver atom with low intensity, and this experiment proved that the spin of electron actually exists that cannot be explained by classical mechanics.
Hello everyone, my name is Mikhail. Here we continue on the conclusion from the experiment. Spin angular momentum cannot take any continuous values but distinct and quantized. As we have shown, total orbital angular momentum of silver atom is 0, which means that there is a second type of angular momentum arising. Just as for orbital angular momentum, we introduced the spin quantum number that can take values from -s to +s, given in total 2s plus 1 values, or orientations of spin angular momentum along one axis. As we remember, we got 2 orientations from the experiment, given s equal to 1/2. Spin is an intrinsic form of angular momentum. Here is a schematic diagram depicting the spin of the neutron as the black arrow and the magnetic field lines associated with the neutron magnetic moment. We are usually given the model that electron rotates along about its own axis. However, there are several proofs that we cannot explain the spin of electron as a motion about its own axis. First of all, neutron doesn't have a charge, so it shouldn't have a spin. However, neutron has a spin equal to the spin of electron. In addition, we usually represent electron as a wave without certain position, and I think you agree it is difficult to imagine wave rotating like a solid ball. One more argument that spin is purely quantum mechanics phenomena is that spin of neutron, proton, and electron are the same. Classically, based on the spinning body motion, we expect that spins of neutron and proton are smaller than that of electron, since they have much larger masses and therefore should be spinning about their own axis much slower. Therefore, we should consider electron spin as its intrinsic property, as we don't know and we also don't know exactly whether it rotates about its own axis or not. Now let's talk about quantum numbers more in detail. First quantum number is spin quantum number S or L depending on the book. Remember that it is a non-negative number. Second quantum number is spin magnetic quantum number MS. It can be considered as projection of spin onto z-axis. It is restricted to 2s plus 1 number of values. From Stern-Gerlach observation, we can conclude that spin of electron is equal to 1 over 2. MS equal to 1 over 2 is usually denoted as spin up, and MS equal to minus 1 over 2 corresponds to spin down. Here are some examples of calculations. Interestingly, that h bar has the same unit as angular momentum, joule multiplied by second, or kilogram multiplied by meter squared divided by second. These are angular momentum operators, which are very similar to spin operators. You just need to change quantum numbers from L to S and from M to MS. These are corresponding eigenvalues that we are going to calculate. The magnitude of spin, we calculate the magnitude of the spin angular momentum for any particle with spin 1 over 2, and we also calculate the component on the z-axis. We can think that these values are pretty small. However, we know that the orbital angular momentum is given by the same formula, changing S to L. So orbital angular momentum and spin angular momentum has the same order, or sometimes they are even the same, so it is not as small as we imagine. Let's look at the representation of spin. Classical representation of spin is an arrow pointing along the axis of rotation. Length corresponds to how fast it rotates. In quantum physics, we never measure zero for the component of electron spin in the x, y, and z directions. So an arrow doesn't accurately represent spin in quantum mechanics. It falsely implies that x and y components of the spin are zero, which is never the case. For an electron, we are only able to measure one of these components of spin at a time, and there is only one possible length that all arrows can ever be observed to have. Z-axis arrow points up or down, but the length is always the same. There is another representation of spin in quantum mechanics. It is described mathematically by two numbers of coordinates. These numbers are eigenvectors. Eigenvectors are shown on the right. Real components are represented by coordinates. You can see a coordinate plane, and this arrow is a spin, and it can rotate taking any possible value, but different coordinates correspond to different probability of spin direction. For example, you can see an eigenvector 1, 0, which corresponds to 100% certainty that z spin is pointing up. You can also see an eigenvector 0, 1, which corresponds to 100% certainty that z spin is pointing down. Spin in each direction has a matrix called the Pauling matrix associated with it. Each matrix has two eigenvectors. Each of them represents one of the quantum states of 100% knowing the spin direction. Random direction is a linear combination of these three matrices. Wave function is given by this expression with C and 1 and C2 to be determined. C1 squared and C2 squared have a physical meaning of the probability of z spin up or down respectively. You can make the same type of wave functions for other directions using corresponding eigenvectors. Let's look at connection with uncertainty principle. Two complementary observables cannot be measured simultaneously if their operators do not commute. So spin operators do not commute. The more accurately we measure one observable, the less accurately we can measure another. If we measure the z direction, if we only measure the z direction, we will always get the same result in measurements. However, if we measure the component in one of other two directions, we lose any information about the z component. After we again measure the electron spin in z direction, we have 50% probability that it will be up or down. How can we imagine spin 1/2 in classical physics? The dynamics of spin 1/2 objects cannot be accurately described using classical physics. In the figure, you can see an object which takes 720 degrees to come back to its initial position by rotation. This is an example of spin 1/2. Also, at the end of this video, you will see a short example with the belt, which also demonstrates spin 1/2. Thank you for your attention, and these are our references. I'm going to give a belt a double twist of 720 degrees. 1, 2, 3, 4. We can see that the belt is totally distorted. Can we undo this twist by simple translation? Let's try. We can see that the belt is not distorted anymore. This is an example of spin 1/2.